So my name is Jonathan, and I'm a PhD student here at the Technical University of Denmark. And I have this PhD project involving the interface between machine learning and quantum computing. I have this agenda where I actually want to take it sort of from a computer scientist perspective. Since I'm a computer scientist, I'm actually not a physicist myself. You can see here that my background is actually in engineering. It's in biomedical engineering with specialization in machine learning. Then I spent a year as a research assistant on pure machine learning or applied machine learning, but only focusing on that. And then last year I got a PhD scholarship in this interface between machine learning and quantum computing. So I also had to get used to a lot of the notation and a lot of the way of thinking and stuff like that. I am mostly interested in what's some places referred to as the second wave of quantum machine learning. I will get a little bit into what that is, but that's more of this near-term quantum computing where we take into account noise and we don't assume that we have any quantum random access memory, and it's more of a hybrid setup. So just to be on the same ground on the machine learning basis, as I know that, or my impression is that some of you know some physics. I'm not sure how much you know of machine learning, so I just want to go through like the basic ideas. The basic ideas is that machine learning is sort of this interface between statistics.
Hey Jonathan, quick interrupt.
Yeah.
It looks like you've got the camera view over top on the top right of your slides. See that box that you probably see?
Yeah. Should I just move it up?
Yeah, move it out of the way there.
Yeah, sure. Thanks. Maybe I can do this.
Yeah, that's good enough.
Okay. So one way of seeing machine learning is that seeing this in this interface between statistics, pattern recognition, AI, and data mining. But the idea is rather that you focus on learning algorithms, which is sort of a different thing from search types algorithms and path findings. There's also this idea that in machine learning, you get gradual improvements as you see more and more data. So let's stick to this example throughout the talk that we have some images, and on these images are cats and dogs. And we can imagine that the more pictures we feed the algorithm, the amount of data, so to speak here, the better it gets at actually predicting whether it's a cat or a dog on the image. Usually we divide the task in machine learning up into three like major tasks. The first one is this called supervised learning, which is sort of a predictive task. The idea is that, again, we are handed some images, and then some humans have labeled them with cats and dogs. And now we want the algorithm or the computer to classify whether there's a cat or a dog on this image. That's sort of a classification problem, right? We have some discrete classes, cat or dog. But we can also imagine a regression problem where we were to predict maybe the blood pressure or something like that, which is more of a number, which is not categorized as such. A great example of this is, as I said, image recognition. And this is sort of the supervised learning. The supervised meaning there has been a human sitting down and actually labeling all the images. We can also think of the unsupervised learning task, which is more of a descriptive task where we want to find clusters in the data. We want to know that despite no humans actually labeled these images with cats and dogs, there still is this underlying pattern of maybe the cats grouped together, they have something in common, and the dogs grouped together. So that's sort of clustering, and then we can also do density estimation, and we can do associated rule discovery, where we sort of discover what's dog often associates with I don't know, with large ears or something like that. And an example of this is detecting outliers in medical data, right? That's a very obvious application. And then we have what's called reinforcement learning, which is sort of this straightforward application is self-driving cars and robotics. I don't want to focus too much on reinforcement learning because I mainly want to focus on unsupervised learning, since the great success of supervised learning so far. I mean, there are still some very hard problems in unsupervised learning that remains undiscovered and unexplored. supervised learning has had very much success within the last few years. So maybe if we were to apply a quantum computer on one of these two, we should go with the unsupervised learning, because that's where there still is some ground to be discovered. We also distinguish between...
Hey, Jonathan?
Yeah?
I know you say you don't want to attend to it, but I was having a conversation yesterday with machine learning and AI and quantum. And can you give me I'm very familiar with supervised learning and unsupervised learning, but
yeah.
Reinforcement learning, can you just give me that little bit why that differs from supervised learning? Because just
sure.
10 seconds.
Yeah. Well, the biggest difference is that you often have, in reinforcement learning, you often interact with the environment, right? So you have a certain rules. This could be a game of chess, and you want to solve the best, given any set of like any state of all the dots you have to move. What's the cleverest and quickest way to actually beat your opponent? Whereas classification task is much more of a you could sort of see reinforcement learning as a sequential classification task, if you will, but reinforcement learning has gotten its own paradigm, because it is this real-time dynamic interaction with its environment. So that's like the main difference. Whereas supervised learning is more of a static. You have a static data set. You might even have a time series, but you don't really interact with the time series as much. You just analyze it. So in reinforcement learning, you actually have an effect on your environment. That's like the main. Was that fine?
Yeah, I mean, that's pretty much what I concluded yesterday or the day before, something like that. I worked it on the side, and I just need to get some examples in my head. One of them, as you've got there, is the exploration versus exploitation. Yeah. I'm just trying to put that in the machine learning. I'm trying to put it into the supervisor or unsupervised box, and maybe I shouldn't be doing that.
No, not right, because it is the
feedback. Yeah.
Yeah. Right. And when I say exploration vs exploitation, I mean think of a chess game, right? You might learn something new by moving some of the pieces in ways that you didn't do before. That's sort of an exploration. And an exploitation is you, with all your knowledge right now, what is the best move? But you also have this uncertainty on, if I actually explore the environment, I might get even better, right? So that's sort of that's sort of a trade-off.
Okay, I think, all right. So I'll do some more digging on that. I think that helped a little bit. I think.
Okay.
Yeah. Okay. Got it.
Would AlphaGo 0 be exploration?
I think there are a bunch of different ways of training it. I definitely think that some authors have explored like how to actually train it. I'm talking about the training process itself. Yeah. But yeah, I haven't done that much reinforcement learning myself.
Okay.
Just to be clear. But that's sort of its own. Yeah. Anyway, there are sort of also two subfields within, which sort of goes between the boundary of unsupervised and supervised learning. And one of them is called this discriminative learning. And essentially, we here want to learn the probability distribution over a label. Again, this could be a cat or a dog, given an image. So we assume that the image is sort of correct. There is no uncertainty in the image. And we want to sort of compress that image into like a 0 or 1, or we want to essentially decide whether it's a cat or a dog. And that over here corresponds to, like, we maybe have some data points over here which are cats and some over here which are dogs. And through discriminative modeling, we sort of learn this decision boundary where we sort of distinguish between cats and dogs. But we could also imagine a much harder task, which is to learn the joint distribution over both the image and the label itself. And that this means that we have to know the probability distribution over all the data, which might seem kind of abstract, but the idea is essentially that we get to put likelihoods on all the data points. And so we could imagine, again, having cats over here as the red one and blue over here with dogs. And then if we were to introduce a new point over here, which is far away from either of the class, we would have a very large uncertainty. We wouldn't really know which class it belonged to. Whereas up here, we would just immediately say, oh, it's a cat, even though that might be an even third animal. So this is a much harder task. And it's also much more interesting because it turns out that there are, at least in the state of the art, there's a lot of people in quantum machine learning focusing on generative modeling because it's a very hard computational task. And that's also what I want to focus on today. So quantum machine learning, what is that? Well, for a couple of years, my impression was that maybe from 2010 to 2015, something like that, that quantum machine learning was getting the quantum computer to do all the machine learning, so to speak, all the data, the inference, everything, and then sort of output that into like a classical interpretation, right? And then the other way around would be, you say you have a system, you have a quantum system, and you can actually control that in a certain way, and therefore we call that control theory and optimization. You want to be able to do something with the quantum computer. But it seems like more over the years, quantum machine learning is sort of all of this connected into one, right? It's sort of that as long as you do some machine learning task and you involve some quantum subroutine on a quantum computer, you can call it quantum machine learning. So even though your model might be classical, if you update the parameters of the model with using a quantum circuit or something like that, you can call it quantum machine learning. And thereby this down here, when you assume that you do everything on the quantum computer, is sort of what's called the first wave of quantum mechanics. Of quantum machine learning. And then the second wave of quantum machine learning is like where you assume that it's a sort of an interactive environment where you, with your classical computer, do all kind of tweaking of parameters in the quantum computer, and then that helps you build some model of the world. So this is what I'm interested in, going both ways, and I will provide one example with all of this, and then one example where I sort of do it from the eyes of optimization and control theory.
Jonathan, I have a question.
Sure.
Yeah, so where would you place the VQEs, the variational quantum eigensolvers? So would they be, would they tune the parameters outside in the classical loop, or do they do that inside the, the quantum loop itself?
Yeah, so the VQEs, I would definitely place in this entire circle right here, right? Because if you use it for a machine learning task of some sort, you definitely solve some sort of classical problem. But if you only work with quantum data and you only infer on the quantum machine itself, you would still need like these control theory and the optimization part, because that's part of the VQ itself, right? You have to have some sort of classical outer loop. So maybe it's sort of some sort of hybrid, but I would say definitely it draws on all of these.
So are you saying it's inevitable to avoid the classical part in the VQEs while training models which are completely quantum? Yeah.
The assumption in VQEs is that you want to approximate some ground state of some Hamiltonian, right? And you want to do that with a variational circuit. And that variational circuit has some classical parameters which you train outside of your quantum computer. So you update your quantum computer with these parameters. And that optimization part is sort of what I'm trying to highlight here, is that draws some inspiration from machine learning, right? Because a lot of machine learning also has to do with optimization itself. So it depends.
Thanks. Yeah. All right.
Now I want to go into like quantum computing from a computer scientist views, and for those of you who know the basic ones, as for example with VQEs, this might be somewhat easy, but hopefully I can catch some of them who maybe is not too familiar with this stuff. Let's imagine that we have a classical bit which can be either 0 or 1. It could also be a coin that we flip to be either heads or tails. Let's imagine that we don't know what the value of the bit is yet. We only know that the probability of it being 0 is p, and the probability of being 1 is 1 minus p. That's all we know of the classical bit. Again, it could be before we toss a coin, what's the probability that we land on heads or tails. Now let's imagine that we could do some sort of operation on this coin. Let's imagine that we can, for example, stretch it in certain directions such that we change the probability of it landing on heads or tails. Now, strictly mathematically speaking, this is sort of can be done by taking this probability distribution x right here, and then apply what's called a stochastic matrix on that x. It essentially just means that we sort of rotate x, right? We generate a new x tilde right here from the original x and the transition matrix. So if you look at the figure over here, it corresponds to like being in the blue state, then applying the S matrix, and then we're in the red state. I'm sorry, the orange state right here. And that's sort of the general idea of quantum computing, in the sense that if we think of these probabilistic bits, we can sort of make it even more general, right? Because before I said that these two numbers here have to be real, they have to be between 0 and 1, and they have to sum to 1. An even more generalized formalization would be to say that they could be complex numbers, as you probably already know, most of you. And now we see the beautiful parallel between probabilistic bits, which is sort of coin flipping, right, and then quantum bits, is that there's both this what's called the wave function, or in the classical sense it's the probability distribution, except that these are not called probabilities anymore, they're called probability amplitudes. And the way that we convert it into a probability, so what is the probability of the quantum bit actually being in state 0, we have to we take the modular square of that number. And just as we had in the classical case, we had a stochastic matrix, in the quantum case, we have the unitary matrix. And that's basically it that we need to know, at least for now. And then there's one more additional fact, which I've written down here, is that before we measure it, the qubit is both 0 and 1 at the same time. And this is like the mind-boggling thing about quantum mechanics, is that things can be two places at the same time or be something else completely. If we assume that we have a quantum computer which can produce, so to speak, any state here, any combination of A0 and A1, then we can actually think of this as a generative model in itself, right? Because now we've created a probability distribution from which we can just look at the qubit, and now we can generate samples from that. So that's sort of why some people have looked at the quantum computer itself as a generative model, as I described earlier. So we imagine that we have this black box quantum computer, which once we measure all the qubits, with some probability we get a certain combinations of zeros and ones. But this combination of zero, or at least the probability distribution itself, we can actually modify by modifying the quantum computer. So some papers has actually been looking into like, what can we do to make the quantum computer itself a machine learning model? And that's quite interesting work, which I just wanted to highlight here. So that's also one approach to go. But now we get into what's called variational circuits. Variational circuits is sort of one of the most popular, I would say, architectures for near-term quantum computers. And the reason is that the thing about near-term quantum computers is that they're very noisy, and you cannot do too many calculations before the information is lost. But people have shown that both experimentally, I'm already skipping ahead here, but down here experimentally and theoretically, they have some great advantages, such that they're actually computational universal. What does that mean? That means that we can take any probability distribution over qubits and transfer it into any probability distribution over qubits. So we have this universal feature. And experimentally, in the sense that we can also easily calculate gradients, how to actually update these parameters. But I'm perhaps getting a bit ahead of myself. What I want to say is that these variational circuits is based on what's called the circuit model of quantum computations. You can do all sorts of quantum computations, but we'll focus on the circuit model. And the idea is that we have these qubits, and we can modify the state of them with quantum gates. And that's the general idea. Just as we saw with stochastic matrices, we now have this in the quantum setting. And the good thing about variational circuits is that if we know out here when we measure all the qubits their value, and we have some sort of objective that we want to optimize or minimize, we can update the angles in here, or the circuit itself actually, from this objective, from whatever we measure, and we can do this repeatedly, and then hopefully at some point these parameters theta right here, they converge, and then we have solved the problem, whatever that might be. And if we look down here, this mathematically corresponds to having a start state. So this is the state that all my qubits are in over here on the left. You can see here I've drawn them as, or this figure is adapted, but these are drawn with where all of them are in the 0 state. And then through P of these gates, I take this state and I transform it into another state. I do that P times in different ways. And then I end up with the output state over here. And then when I measure them, I actually sample from this distribution right here. So now, let's leave that aside for a moment and maybe just ask if there's any questions or any comments on this. Good. I hope you, if you have something, just go ahead and let me know. If we leave this for a side and just keep this in the back of our head, we can now start to ask what kind of interesting problems can we solve. And for that, I wanted to focus on the restricted Boltzmann machines, because that is one of the most, I think personally, interesting cases for near-term devices. And that is, people have tried to look at the restricted Boltzmann machine, which is actually an old model. I will introduce it in a moment, but it's actually a very old model. It's a very small model, which due to its smallness, we can actually do some interesting thing with the quantum computer on it, simply by its size. And now I want to explore all of these ideas into one specific approach. But before I do that, I want to introduce the restricted Boltzmann machine. So we imagine that we have what's called a Boltzmann machine that is a 2-layer neural network. It can actually be more layers, but we just assume for now that we have 2 layers. And we have what's called the visible layer, and we have what's called the hidden layer. And the visible layer is sort of where we encode our data. So that's our encoding part. And then we want to be able to compress this information onto the hidden units. And all the theory behind this shows that if we are able to do that, then by putting in random values at the hidden units, we can actually generate, by backpropagating, or propagating the other way basically, we can generate samples that resembles the data that we just updated our machine with. So just to be a little bit more formalized, we have some samples V here that follow some probability distribution. That's sort of exemplified here. And then we will assume that first of all that V is a binary vector. So let's say over here that we have 4 different entries for our visible units. This means that we can get many combinations. To be more specific, we can get 2 to the 4th different data points, right? I can construct a bit string of 0s and 1s on the length of 4. I can do that in 2 to the 4th different ways. So we can imagine that all of these heights you see here is sort of the probability of that data point occurring. And what we want our Boltzmann machine to learn is that probability distribution. How many times did 1, 1, 0, 1 occur, for example? And now these restricted Boltzmann machines has what's called defined energy function. And this energy function comes in quite handy when we want to know what's the probability of observing a certain combinations of 0s and 1s, both on the visible and on the hidden layer. So this restricted Boltzmann machine right here has this energy function, where the V's and the H's here are the visible and hidden units respectively. And then this W right here is sort of the interaction term that could be seen as these dots, right? I'm sorry, these lines connecting these dots right here. And then they also have what's called a bias. So that's just the value itself multiplied by some value. And then when we can put in all combinations of V's and H's, and then we can get an energy for each combination of V's and H's. But it turns out that the probability distribution, which is the same as saying what's the probability of observing exactly this combination of V's and H's, can be written with respect to this energy function right here. And I want you to pay close attention to this equation right here, because we're going to see something very similar soon on how we can actually use a quantum computer to sort of make a distribution that looks somewhat like this. The Z right here is a normalization factor such that this probability distribution integrates to 1. But just keep in mind this, this form right here. This machine right here, this Boltzmann machine right here, is, as I said, a generative model. And the way that it's trained is through something called Gibbs sampling. A specific type, namely called contrastive divergence. And Gibbs sampling in itself is actually quite computationally hard to do on a classical computer. You have to do all kinds of sneaky tricks, for example, Monte Carlo sampling. And this is where, at least the idea is, that quantum computers can come in and help, is where some of these computationally hard tasks lie. In the quantum case, we now assume that each neuron here, each of these circles, are spins. And as you know, just as we had the energy function before, in quantum mechanics, we don't have a function as such. We have what's called an operator. And specifically for the Hamiltonian, that's called, I'm sorry, specifically for the energy operator, that's called the Hamiltonian. And you can see that it has the exact same form. The only thing that I've changed is that I've changed these V's and H's onto operators, which is like saying I now measure the ith qubit in the Z basis, and I now measure the jth qubit in the Z basis. And the way I calculate this energy function when I've measured all the qubits is that I plug those values in here, and then I calculate the energy. But now we see something very nice, because it turns out that if we take the qubits and we have this energy operator over those qubits, and we make it interact with an environment. So imagine that we have a quantum computer where everything is guided by this Hamiltonian. We imagine that. And now we let it interact with an environment which has what's called the temperature. It's not as such like a temperature like measured in Kelvin or something like that, but it's sort of an effective temperature, and there's a very rich literature on that. But just think of it as a temperature for now. And if we do that and let the system reach equilibrium, meaning that a certain time has passed, it actually turns out that the qubits are in a state that looks just like this. And now we see perhaps the connection between the quantum part and the classical part, because if we can prepare this state, we can just look at the qubits and update the weights and the biases, all these W's, A's, and B's, simply instead of doing Gibbs sampling on a classical computer, right? So we actually still do Gibbs sampling, but now we do the sampling on a quantum computer. And here I want to emphasize that the model is still classical, but when we update the weights and biases, we do that by sampling from a quantum state. So are there any questions so far? Because this is I know this is a lot of equations, and maybe it's a bit confusing with all of this. So I would really like if you have some questions, just go ahead and hit me.
Yeah, I have a question. So can you talk a little bit more about the relative entropy graph which you can see here? Yeah, sure.
So let's try to remind ourselves what is the actual goal of this machine learning model that we have over here. The actual goal of this is to make sure that the probability distribution over the visibles come as close to the real data as possible, right? So we observe some data, and then we feed that to the model, we let it train, and then at some point we stop letting it train, and now we ask, what are some of the likely visible values that we just saw? And the way that we do that is by the thing that I showed on the last slide down here, is I see what is the probability distribution over V and H. But this task right here of making these two approximating each other, or in fact making the visibles approximate the data, could be the same as minimizing the relative entropy between the visibles and the data. So that corresponds to, you can see here that for each of these probabilities right here, you can see that where they are very different, the relative entropy is large. And so you can sort of make the analogy that this task right here corresponds to minimizing the relative entropy between the data, the P data right here, and then the visible units, right? So this is sort of a distance measure between the visible and the data, and you want to minimize that distance, because if you minimize it, then you solve the problem.
Yeah. So this cross entropy loss that we have, the loss function that we have defined, can we optimize it using a quantum optimizer, or do we have to do it with a classical optimizer?
Yeah, so it's actually pretty hard to do. And there are all kinds, you can look at this paper if you're very interested in this, how it actually can be done, how you actually sort of approximate minimizing this, because it's actually quite hard to minimize it directly. But the idea is sort of the same, right? That you make some sort of loss function that you minimize. And even though it's hard to minimize the relative entropy directly, you can do sort of bounds on it. So you can minimize a bound instead of the function itself. Yeah, but great questions. Now comes the big question, right? How can we prepare these thermal states? And again, just to recap here, the thermal state was this state down here, because this is what we actually want to prepare. And this is what's very interesting, both from a quantum information perspective, but also from a machine learning perspective, is how can we actually approximate that? Because that's actually quite hard to do. I want to mention one approach, which is some guys from, I'm pretty sure they're from Canada and the US, who sort of uses QAOA, which is a specific variational circuit architecture, to approximate this thermal state. And you can show that if you prepare your qubits in a thermal state of some different easy Hamiltonian, and when I say easy, I mean, if you look here, this right here has a lot of components, and it's actually quite hard problem to solve. There's a whole lot of rich literature on quantum Ising models and how to actually solve it. It's actually quite hard problem to do. So that's sort of a hard Hamiltonian to reach the thermal state of. But you can also define something else that is much easier. For example, only having these biases on each qubit. And so they show, Jerome here, he shows that if you prepare your qubits in a thermal state of some easy Hamiltonian, then you minimize the expected energy of the Hamiltonian, and that you can do by variational circuits QAOA. Then you actually approximate the thermal state of your complex Hamiltonian. So if we look over here to the right, you can imagine that our qubits are now in this state right here, and we want them to reach this state right here. And if we do it by what's called analog adiabatic, it's like that corresponds to like a very, very slowly turning all the parameters in the quantum circuit in a specific way, and then we would definitely end up here. But this is a very slow and theoretical thing. It can be done, but it's very hard to do. You can also simulate it. It's sort of the same way where you literally just cut this long road into several small pieces, and then you take very small steps. Or you can simply brute force it with QAOA and just take few but large steps, and then hopefully you end up in the state that you want, such that you can train your Boltzmann machine. And that's exactly what Jerome he does, at least in approximative way. Down here, I've shown my simulation of the exact same thing. So what I've done here is that I have the circuit, and then I train the and then I train the Boltzmann machine, and then after it is done training, I can put all sorts of noise on the both during the training, but also put noise on the data itself. And what I see is that the what's called the mutual information, and we can merely think of the mutual information as some sort of distance measure between two things. And I see that when I have very little noise, I have a very large mutual information between the truth, the ground truth, and what my model predicts. So it converges nicely, and Jerome, you can look at this paper if you feel like it. He has some nice figures also. All right, this was sort of one of the interesting, at least I believe, aspects of near-term quantum devices, right? Is that can you prepare interesting states for your qubits that you can use constructively to either as a generative model itself, as some papers have shown, or use the samples from it to update some classical machine learning model. That's sort of one way of doing it. But you could also think that for these architectures, we have specific quantum circuits that are designed in specific ways. For the QAOA, for example, you saw here that we have to make a certain number of steps, right? But how do we determine how many steps we should take? Should we take 5? Should we take 1? Should we take 100 steps? Because we should remember that on near-term quantum devices, the more steps we take, the more information we lose. Every time we do one burst of calculation, we lose some information. Simply because of decoherence. The qubits sort of lose the information that we got. But a natural question comes up, how do we actually design our circuit? How many qubits do we need to encode our data? You can say the data comes with a certain number of dimension itself, but you could maybe imagine that you could reduce that cleverly. Or how do you design how many layers in your circuit, or how large P should be? And that I looked into recently, where I used what's called Bayesian Optimization for circuit design. Again, this is sort of a classical way of thinking. So I just want to quickly recap exactly what Bayesian optimization is. I just need to look at my watch. So Bayesian optimization is sort of mostly focusing on this part right here. This is sort of the optimization, the control theory and the optimization part of the quantum computer itself. But it's again tied together with all of this, where we actually want to solve some intelligent decision process or generative process in terms of machine learning. The term that we use for all of these parameters, like for example, the number of hidden units in the restricted Boltzmann machine, how many hidden units should I use? How many circuit layers in my QAOA should I use? What should my training batch size be, and so on? Those parameters we actually call hyperparameters, in the sense that the parameters themselves are what's in the circuit or in the model, and then the hyperparameters is what sort of constructs the architecture of the model itself. And we can think of Bayesian optimization as this tool that lets us find all of these in a clever manner, in a probabilistic manner, which is well defined. And if we look on to the left here, I have a grid where I have an underlying probability distribution, and now I'm handed a bunch of I don't see the colors yet. I only have point estimates. I only have all of these numbers here, and now my task is to click on this, and then I have to find the maximum of this function. That corresponds exactly to this over here with hyperparameters, right? Because essentially, in the end, what we want to reach is sort of the best machine learning model. But the best machine learning model is quite hard to train, and it takes some time and so on. So it's quite expensive to train. And therefore, we want to make very clever decisions on which hyperparameters we choose. So once we've chosen those hyperparameters and we get some outcome, we want to also be able to make a clever decision of which hyperparameters do we need to check for next. To be a little bit more formalized, we can imagine that we have what's called a search region S, and the search region here would corresponds to like this axis right here, and then this axis right here. This is my search region, this entire space. And now we want to find the X, and in this case, that is sort of the combination of this right here and this right here, i.e. a point on this search grid that minimize some function. And the function itself can even be probabilistic. And what does that mean? That means that even though that we query the model with a certain number of hyperparameters, if we do that multiple times, we might get different estimates on the cost function itself. We need to be able to take that into account also. I don't know how much time I have. I can see that I've used maybe 40 minutes or something like that. Tyrell, do you think there's time for a demo?
Well, I don't think we're time oriented here. I think it's more important you get the good good material keep flowing. So,
Okay,
like,
awesome.
you know, if, worst case, if somebody needs to drop, they can drop and pick it up on the recording.
Awesome.
So.
I need to say new share, and then it's right here. Can you see this guess the optimum screen?
Nope.
Shoot.
Yes.
Good.
Got your browser.
Thanks. Yeah, it's my browser, exactly.
Yep.
So this is a demo developed by one of the folks in our research group, one of the classical machine learners, so to speak. And the Bayesian optimization can be very well sort of thought of in this experiment right here, right? Because the task here is to find the optimum of this f, and we are only given these 9 points. Now I can click somewhere on this search region, and then I can say, what was the f function right here? So now I submit my click, and then it thinks. And then I say, oh, I get 1.6, and up here it was 3.5. So maybe the optimum is up here instead. And I could do this a couple of times. And in this case, he wants us to guess 5 times. And then hopefully my algorithm, my Bayesian optimization scheme will find the best hyperparameters that actually serves the task that I want to perform. So now let me just go back here onto my slides to say that what we actually need to be able to do all of this. And what we actually need is what's called Gaussian processes. And this is a very rich area and is very complicated. So I just briefly want to mention what the idea is. The idea is, again, that you can look up here onto the top right corner up here, that we have a search space. In this case, it goes from 0 to 1. And for now, we have asked the function, or the if that you saw before, about a point right here, 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 and here. So the Gaussian process tells me that at the points that you've sampled, the uncertainty is very low. But at the points where you have not sampled, the uncertainty is very high. And you might find an optimum in this region, but you might also find an optimum in this region. If you want to do another query of your hyperparameter, we can use what's called an acquisition function. We can use what's called an acquisition function to determine which hyperparameter do we want to ask for next. And you can see that different acquisition functions, here's called the PI and the EI and the GP-UCB, they ask for different hyperparameters depending on what kind of settings that you give. So what I want you to think about is that when we have a quantum circuit and we need to define how many layers, how many qubits, how many, like all of these sort of the batch size, all of that, one way of thinking about it is like thinking about it just as a machine learning model in itself, and then make these clever choices based on quantum processes. And the clever processes comes into when we can take all of the things that we know so far and ask our Bayesian optimization algorithm, which one should I try next? And that's the whole idea of this. And there's a bunch of equations there if you're interested. And you can see here there's a very great demo if you're more interested in like Gaussian processes. It's a very interesting topic. So let's try to do this. Let's imagine that we have a data set which is as many dimensions as we would like. In this case, I'm only showing 2 dimensions, and then we have 2 classes right here. I know I started the entire talk with saying that classification and regression problems is not interesting for near-term quantum computers, but just play along here, because here we want to show that you can actually do Bayesian optimization regardless of the task. So the idea is now that how many components, this is the first component, this is the second component, you can also imagine there's a third and a fourth and up to a certain number. How many components do I need? That's one question I want to ask. And the second question I want to ask is, how many layers in my circuit do I need to be able to classify blue from red in this case? I've sort of summarized it down here, but just to take a step even further back, we can see that all of these here are floating points, right? All of these numbers here, the first component here is guided between 0 and 1 and can be everything in between. So you can go about, if you're in the quantum world, you can go with 2 settings. You can either imagine that you are able to perform an arbitrary rotation of your qubit in some direction. Let's just use the X direction, for example. So now you apply, before you apply your QAOA circuit or your classifier or whatever that you have, you apply a rotation gate on the first qubit. Let's say that we want to encode this data point right here. Then we apply a 0.2 rotation around the x-axis on qubit 1. And you can imagine doing the same for qubit 2, depending on which data point that we want to encode. So this is how one way of encoding it. Another way of encoding it would be to sample each component. You can see here that I've normalized all components to be between 0 and 1. In that sense, we can sort of think of it as probability. So instead of encoding our qubits as with rotations and superpositions, we can encode them as either 0 or 1, depending on what our sample here turned out to be. So that's sort of 2 different ways. I'm going to use the superposition encoding, but you could do both and then just average over many iterations. Then I use TensorFlow Quantum. I saw that you had Amira Abbas as one of the speakers maybe a week from now or so. And she's going to talk about Qiskit and Penny. And Qiskit and Penny is sorry?
That was this morning actually, and check
okay.
Palooza. Yeah, she's got another thing on next Tuesday morning, 9 a.m. New York time.
That's awesome.
Yeah,
that's
very
awesome.
good talk, by the way.
Yeah, she's very good. I think I've seen some of her stuff on YouTube, and yeah. Anyway, TensorFlow Quantum is just like that, just built by Google instead of IBM and Xanadu. So I use TensorFlow Quantum, and then I use scikit-learns. Everything is done in Python, by the way, and you're more than welcome to see the script if you want. Everything is done with TensorFlow Quantum and what's called scikit-learns optimized GP minimized. So actually, it turns out that the code is only a few lines down here, as you can see down here, except for this train circuit function right here, which is several lines, because that's actually our F, as we saw before, right? Remember that the whole Bayesian optimization was about finding the best F. So this train circuit actually trains an entire quantum circuit to classify blue from red, and then it evaluates it on a data set that it hasn't seen before, and then it returns that to the GP minimize function, and the GP minimize function then wants to find the best accuracy on this data set right here. So that's sort of the task, and you can see how easy it is that you only define your search space. So you can see here I define what's called the N, that's the number of qubits, right? That's the number of components I want to use, and then I define L, which how many layers in my quantum circuit do I need. It's very easy. You just plug it in, and then you call your function itself here, and then you call your search space here, and then all the rest of these can be just used by default, but I've actually chosen to use them myself. But essentially, that's it when you do Bayesian optimization. So I want to show you the results. This is the posterior mean over the hyperparameters. So again, I defined this search grid. I defined from 1 to 10 on each hyperparameter. And then I let the algorithm, the Bayesian optimization scheme, I let it ask and train 15 times. And hopefully, I mean, not hopefully, but it does it. It does it in this optimization procedure, this Bayesian optimization procedure. And what we see here is that when the circuit only has one layer, then it doesn't matter how many qubits there is, the accuracy becomes very low. This tells us that the quantum circuit itself is not expressive enough to actually being able to classify regardless of how many qubits that you have. Whereas if you increase the number of layers to 2 and above, you can see that the accuracy increases dramatically. And so from this right here, I can also show it in 3D. It's a bit more fancy, but the idea is so to speak the same, that we generate this landscape, and then we want to find on a validation set that the algorithm hasn't seen before, which of these hyperparameters are the best. And then we use those hyperparameters to get an a data set to train on a data set that has never seen before, even on this validation scheme right here. So that's the test error. And I obtain in this, I know it's a synthesized data set and all, I obtain a an accuracy of 95%. And that may not tell us very much, except when we compare it to what a classical algorithm would do. The idea is completely the same. In this case, I use another classical machine learning model called a support vector machine. And don't mind what that is. It's just a machine learning model trying to classify blue from red. And you can see that for that model specifically, it doesn't really matter whether it gets 1 bit or 2 bits or 3 bits, even up to 10 bits. It gets the same accuracy right here as we just got before. If we use a classical neural network, which also has a number of layers, we can see that if we take the best classical neural network and train that on totally unseen data, then we obtain a slightly smaller test accuracy, but we have no, we cannot say if this is statistically different from the other ones. So the remarks comes as follows: that the goal of this little tutorial here was to implement a Bayesian optimization framework for estimating the best circuit size. And when I say size, I mean both how many layers and how many qubits. The idea was to take this toy classification example itself, which might not be interesting, but the framework is validated, which was the entire point. It could also be interesting to optimize for other hyperparameters. As I said, batch size, learning rate. We just need to keep in mind that every time we do this, it's very expensive. So it takes more and more hours as you increase the number of parameters, and also you increase the search grid. A more fair comparison would actually might to these classical methods might be to do multiple trials, cross-validate even for different test sets to get instead of, I just go back here, instead of getting 1 point estimate of the test accuracy, we can perhaps get a small distribution over the test accuracy. And then we can ask, is that distribution significantly different from the other ones? I mean, we have no reason to believe that it is, but that would perhaps be more fair if we actually want to compare the two. Yeah. Then, as I said, this example in itself might not be interesting, but one of the things that I'm looking into right now is for which problems is it interesting to apply these Bayesian optimizations to fit hyperparameters. And for that, I'm currently looking into unsupervised learning, which I discussed previously. So how can I actually learn, say, a thermal state by using a better circuit than perhaps Jerome does in his paper? That's one way of thinking of it. But also something that I've completely ignored until now is that the NISQ devices so far, the near intermediate scale quantum devices so far are very noisy in itself, as I said. But very, very few papers, including my own work, has sort of ignored this noise until now. But if we wanted to do more realistic simulations and incorporations, we have to include more realistic noise models. And IBM, if you go into IBM's webpage, I think they explain their specific noise models. And it's a very interesting topic, but it's also very complex, and how you can play around with these. And as I say again, if we really wanted to test the robustness, we have to use, perhaps search even better classical models and methods. So now I want to end here with some open questions that perhaps no one knows or is trying to figure out. And the one current research question that is that will we ever get a scalable quantum computer? Because it's very hard to build. And when will it come? That's a very open question. It's very interesting. I believe that you all saw earlier this year that Google obtained quantum supremacy, or was that last year? But recently they obtained quantum supremacy for a very specific problem, but we've not reached practical quantum advantage yet. And also people talk a lot about, and you see papers even coming out today, that a lot of papers assume what's called quantum random access memory, but we don't even know whether that would be built yet. But still a lot of papers right now are assuming this, and then they do all the theoretical stuff behind, which is quite interesting, but we never know whether it's actually going to be used. So that's also a very open question. And as I said, today's quantum computers are small and noisy, with many experimental errors, and the question is that what are the limits to those? We really don't know that yet. We really don't know their expressiveness yet, because these variational circuits are no more than a couple of years old. I think they're from 2014 or 15. That is the idea. Then also, very few papers actually compare with the best classical approaches, but some do, and it's quite interesting to if you're interested in it, to look at this paper where they use sort of finance applications, and they actually, in this specific case that you're testing, they actually beat the best classical model, which is quite interesting. And then I also want to mention that a lot of optimism exists for this NISQ-era, but most of you might be familiar with John Preskill, who's like one of the main leaders, main thought leaders in quantum information science. He predicts that the 100-bit quantum computer, which is sort of this NISQ-era tops, will not change the world right away, but we should regard it as a significant step towards the more powerful quantum technologies of the future. Then current research also tries to use what's called error mitigation, and here they actually do use and simulate with the errors and with the noisiness. That which is actually shown to improve training of quantum circuits. And maybe some of the hypotheses are that maybe this noise can sort of be some sort of a regularizer or something like that. That's a very interesting field at the moment, I think. Yeah, and then I also say that incorporating realistic noise models and running on actual hardware seems inevitable, meaning that if we actually want to use these near-term devices and not just simulate everything, we need to start coding on actual devices. And very few papers do that, including myself. I haven't run one, I think, or maybe I did it once, but it's very fun to do, actually. So you should considering it if you want to go into this field. And then lastly, the big open question that no one knows, but we really no reason to believe, is that can these NISQ devices provide any advantages at all for classical data? Some think so, and some have said that there are no argument for that so far. I think that the best and most encouraging view is to say that we don't know, so we have to figure out. But yeah, that's like the big main open question, or can these NISQ devices only work for quantum data itself? That's like the $1 million question. Yeah, so thank you very much. I hope I'm on time.
Hi Jonathan, I had a question actually.
Awesome, thank you. Go ahead.
I was wondering regarding this Bayesian optimization, does it also has an inherited quantum feature mapping of classical data? Because I was wondering, the data you had presented, it was like not very separable, linearly separable. So
yeah, you're thinking like in terms of kernels, or like a high dimensional space, or
yes. Feature space, the quantum feature space.
Yeah, no, not really. I mean, not as far as I know. I mean, my guess is that it doesn't really encode anything in a higher dimensional space, except that, the very nature of qubits is to encode information in a high dimensional Hilbert space. But I have no reason to believe why, it would actually use this. That way we would have to go into like quantum kernels, which Maria Schultz has done a lot of interesting research on. You should check her out. But yeah, I think that's my best answer.
Mm-hmm.
Okay.
So Jonathan, me and Raghav are actually working on a problem statement for classification of digits.
Okay.
Basically classifying images. We are trying for 4 and 9 digits, because it's pretty difficult, and we are trying it in the in the third dimension with 3 feature spaces. You know that the size of the image is 784, right? So 28 cross 28, that gives you 784. We are compressing the features to 3, and then
trying out with the MNIST data set.
Yeah, the MNIST. Yeah, I was going to ask if this is the MNIST. Yeah, I get that. Yeah.
Yeah.
Have you seen TensorFlow Quantum has actually done this?
Yeah, I've seen that.
Yeah, I've seen that. but we were trying to implement it on the
With
feature
Qiskit.
map. Yeah, with going with all the scratch from the scratch with the variational quantum circuit and feature mapping.
Okay.
So,
So
that's
we
where
somehow
were
came
stuck.
to a conclusion that the ZZ feature map with certain customizations will be better. And you know, like we have custom feature maps in Qiskit, like real amplitudes and efficient S2. We were trying those, and we'll surely use your you know, the Bayesian
With the Bayesian
optimization. We'll get back to you on
optimization.
that. Yeah.
Yeah.
Okay. Okay.
Yeah.
I mean,
Thank you
that
for-
sounds quite interesting. Did you have you put anything online, or like
No, we haven't put anything online yet.
Yeah, not yet. Maybe we'll put it out. We
We
were
can put
actually
up
able to
some-
get some 75% accuracy on it. So
okay, and did you know that TensorFlow Quantum does a lot of pre-processing, right? They they take the image and shrink it down to 4x4, and then they remove contracting, like they remove 6s and 9s, I think, or something like that.
Right. But we were trying to do it from ground up, from scratch.
exactly.
Yeah.
Okay, yeah. Yeah, but it's very fun to play around with, I think, and hopefully you get it to work soon.
Right. It's fun to work on the base, the scratch level of the circuit.
We'll surely get in touch with you.
Sure.
When we need
Yeah, go ahead. I
Bayesian
can maybe leave
optimization.
my, let me just see. I can maybe leave my email and stuff up, or you can maybe just find me online. But my first slide was actually all my information. Yeah, you can just go ahead and email me or find me on Twitter or on LinkedIn, whatever.
Sure.
Okay, great.
Hey, Jonathan, I got a question.
Sure.
Just because somebody's going to ask me, I'm sure within the next few days. So in the machine learning community here, quantum, so IBM has now gone out on record saying in 2023 they'll have an 1100 qubit machine, and you know, obviously no commitment on the noise level and all that, but let's just say
no.
So,
I was gonna say.
yeah, but so from a machine learning guy's perspective, when we say that, what registers in your mind? It's like, okay, great, or not, or doesn't affect me in my world very much, or yeah, okay, well that means I probably might be able to do this, something like that.
Yeah,
is there any delta?
I mean, the current bottleneck right now is that I cannot simulate anything above 20 qubits, maybe even only 14 qubits on my laptop, and if I go to a cluster, maybe up to 30. So there's definitely some advantages there where you can exploit much more, like much larger Hilbert space that you cannot do classically, and therefore I'm looking very much forward to it. The only thing that I'm concerned about is that current noise levels are so bad that, you know, even inverting a matrix cannot be done or something like that, you know. So I hope that the focus is also on like decoherences time and stuff like that. But you know, it's always fun to play with these systems, and so I'm very optimistic. That's like my short answer. I'm very optimistic, but I would be very careful in saying anything about, you know, whether we will see huge applications. I mean, I hope so.
I mean, would it signal to you like, oh wow, yeah, okay, so that one algorithm or that one technique I'm thinking of, I might be able to do it now, you know.
Oh, yeah,
forget the increased state space and stuff, but it's like, you know, it's, wow, I might be able to do that now or 3 years from now. I mean,
yeah.
I mean, I have a model in my head that if you got, let's say 50 qubits and you got an algorithm or a circuit that works on 50 qubits, you know, more is great, but your algorithms, your technique isn't really going to change much. That's my mental model. Now it may be classical thinking and I'm missing something, or you know, just wondering.
That's a good question. I don't have a model in my mind where I think that if I had 1100 qubits, I would be able to do all kinds of stuff. But I mean, it also depends what they mean by 1100 qubits, right? Because is it 1100 physical qubits or is it 1100 logical qubits? Can I actually manipulate, 1100 qubits, or does it take 400 or 200 or 100 qubits to like actually provide one logical qubit? So that's kind of a deal breaker in terms of how many actual logical qubits can I actually program, and are all the other ones just used for error correction? That's like a huge question I have.
Yeah, I mean, it certainly has goodness associated with it in any way. I mean, whether they're noisy or not, but I mean, it's not like, oh, good. Now I can, divide 4 by 2 now. Yeah. Or whatever. And
let's see. I mean, I've only come up to, and the community so far has only simulated very small systems, and we have, we don't know really, I would say at least, I don't know what would happen if we were to simulate hundreds, 500 or 1,000 qubits, and not simulate it, but actually run it. I mean,
just curious.
Yeah.
Could you share your references, please?
Yeah, sure. I mean, maybe I should just share my slides somewhere, but they are in the bottom.
That would be easier if you don't mind. I could just stick them up in the space. People know where to look.
Yeah.
He's an academic. Of course he's got, citations and references. Absolutely.
Yeah,
I mean,
I asked because you mentioned some papers a bit too quickly for me to write them down.
Yeah.
Sure.
Thank you.
Sure.
Yeah, Jonathan, if you could send me, if you're okay with that, send it, and then I'll put it in a normal spot. You guys should know where that is.
Yeah,
cool.
Thank you.
Okay.
Thank you so much for inviting me. It was a pleasure. I really like the interactions from all of you. So I hope you enjoyed also.
I did, certainly, and this is one of those, I'll put it on my list. I know I got something going on Friday where I need to be more conversant in this, and so I'll be watching the video because I know I'm missing 90% of it.
Oh, okay. That's a lot.
Well,
I hope the rest don't miss 90% of it. I hope that you got some takeaway points.
Well, I got
this was a wonderful
points.
talk, Jonathan.
Yeah.
Sorry?
This was a wonderful talk, Jonathan. Thanks.
Thank you.
Got to learn a lot.
So at the right level for what I need anyway in my space. So.
Awesome.
Yes, much appreciated. Thank you.
Yep.
Thank you so much. Thank you.
Thank you for bringing Bayesian optimization up. We'll try that out.
Yeah, sure.
Thank you.
Sure, go ahead.
Give credit where credit's due. Don't forget. Amir, you showed up all of a sudden too. Not to change the topic, but good to see you.
Yeah,
Jake, you're here too. All right.
I caught the tail end. I'm gonna have to watch the front end of the talk on YouTube. But yeah, seems like it was a great talk.
Yeah, actually, we were talking about Adabas. No, were you in that talk this morning with Amir Adabas?
Yeah, Amir Abbas. Yeah.
Yeah. Amir, were you there? Maybe not. You were. Oh no, last night's talk you were at. That's right. You were asking questions last night in Portland. Anyway, I digress.
No, I'm curious now. Amir Abbas gave another talk. Where was this?
Dude, Quantumapalooza.
Oh man.
You got to look at it all the time. There's 3.6 events every day. Sometimes there's 12 or 13. So next Tuesday, she's doing a series of 3. Today is number 2.
Who's doing the 0.6 one? Oh, okay.
That's average, dude. It's average.
Yeah, I know. I was kidding.
I know, wise guy. I should be using mean.
Yeah.
Or actually mode would probably be better. Anyway, Quantumapalooza Tuesday, I forget what we were talking about, but and I think they are recording it. Just check Quantumapalooza with the history. I'll put the links in there. But yeah, she gave a great talk. She went through Penny Lane and stuff like that today. But she'll be back again on Tuesday next week, 9 a.m. New York time. But dude, check Quantumapalooza, man. You know how much work it is putting all this material out there on that website? You guys better be watching that thing. There's a lot of activity. There's a lot of activity.
Yeah.
Okay. Posted. What's posted? Yeah. I think I think so, because I said to myself, oh, I got to watch this one again too. Today's like a machine learning day. So I think they are. But the trick is check Quantumapalooza for last Tuesday and see if I put that up. And usually it takes a couple days till I get the link. I put it up as soon as I get the link, but sometimes it takes a couple days for people to publish it. But yeah. All right, guys.
Thank you so much.
Guys, thank you, Jonathan. Have a good night. Sleep
You
well
too.
tonight. Good
I
job.
will. It's getting dark.
Getting
I
dark.
know it's not too bad. It's not too
Dude,
bad.
it's only 8:30. The sun's still there.
It's Denmark. It's
Yeah.
dark all the time. Yeah. Anyway.
All right.
Have a good one.
All right. Thanks again,
See you
man.
guys. See you guys. Bye.
See you guys later. We got AWS tonight, by the way, 7 o'clock-ish. 30 days in. I've got something I want to share with you.
All right.
About
Cool.
AWS
Yeah,
tonight.
sure. All right.
See ya.
Cool.
You'll
Bye.
be asleep, Jonathan. See you later. All right. See you guys later. Tonight, AWS. Good conversation. I hope. See you, George.